Section 8. Elements as a sidechain. Elements is an open source, general-purpose blockchain platform that can also be pegged to an existing blockchain such as Bitcoin's. When pegged to another blockchain, Elements is said to be operating as a sidechain. Sidechains enable the two-way transfer of assets from one chain to another. Implementing Elements as a sidechain allows you to work around some of the inherent limitations of the main chain while retaining a good degree of the security provided by assets secured on the main chain. While a sidechain is aware of the main chain and its transaction history, the main chain has no awareness of the sidechain, and none is required for its operation. This enables sidechains to innovate without restriction or the delays associated with main chain protocol improvement proposals. Rather than trying to alter it directly, extending the main chain protocol allows the main chain itself to remain secure and specialized, underpinning the smooth operation of the sidechain. By extending the functionality of Bitcoin and leveraging its underlying security, an Elements-based sidechain is able to provide new functionality that was previously not available to users of the main chain. An example of an Elements-based sidechain in production use is Blockstream's Liquid Network. In order to initialize an Elements blockchain as a sidechain, we need to use the federated peg script parameter. This parameter can be set in a node's config file or passed in on startup. The federated peg script defines which members of the strong federation can perform peg-in and peg-out functions. These functionaries are referred to as watchmen, as they watch the main chain and sidechain for valid peg-in and peg-out transactions, and action them if valid. To peg out means to move pegged assets out of the sidechain and into the main chain, and to peg in means to move pegged assets into the sidechain from the main chain. When we say move into the sidechain, what we actually mean is the funds get locked in a multi-signature address on the main chain, and a corresponding amount of the asset is created on the Elements sidechain. When we say move out of the sidechain, what we mean is that assets are destroyed on the Elements sidechain, and the corresponding amount is released from the locked funds held on the main chain. Permission to perform peg-in and peg-out functions requires that functionaries prove ownership of the public keys used in the federated peg script. This is done with the use of the corresponding private keys. In order to create a federated peg script, we therefore first need to have each of our nodes generate a public key. We also need to store the associated private keys for later use, as we'll need to wipe any existing chain data and initialize a new chain using the federated peg script. This is because the federated peg script forms part of the consensus rules of a sidechain, and it cannot be applied to an existing non-pegged blockchain at a later date. So, using the same setup as we did in previous tutorials with two nodes, E1 and E2, let's first generate an address with each of our nodes, store the relevant data for later use, and then generate the federated peg script, which we'll use to initialize our sidechain later. So first, we need each of our nodes, which will act as the watchman in our network, to generate a new address. So first, let's do this from E1. So to do this, we can type E1 CLI get new address. And let's actually store this in a variable to make the rest of the tutorial easier. So let's put this in a variable named E1 underscore addr, short for address. Let's run that. and we can print out that address just to see what it looks like. Perfect. Now let's do the same thing, but we will generate an address for E2. Perfect. Now we have generated an address from E1 and one from E2. Next, let's grab the public and private keys from this address, and we'll use this information to create our fedpeg script. That is what we need to use elements as a sidechain. So, to get the public key from these addresses, the public keys, let's run E1 CLI get address info, and let's pass in the E1 address. Perfect. So right here we see a whole lot of information. Let's highlight this public key field. That is what we want. So let's save that into a local variable called E1 underscore pub key. And we will be using that in a bit. And similarly, let's grab the public key from E2's address. So we can run E2 CLI get address info E2 underscore address. Perfect. Now from the second address, we have also gotten a whole lot of information. Let's copy the public key that is listed here and save that into a variable called E2 underscore pub key. Perfect. Now what remains is we also need the private keys from these addresses. So let's get E1s by using the dump priv key RPC with E1 CLI dump priv key, E1 CLI dump priv key, and we can just pass in that same address. And let's actually put this result into a variable called E1 priv key. Let's execute this and print out the result just to confirm that it worked. Perfect. So we can now see E1's private key for this address. And lastly, let's run this same command for E2's address so that we can get E2's private key for this address. Perfect. Now we have stored the private and public keys from both of these addresses for later use. All right. Now what we'll need to do is wipe this existing elements chain and wallet data and initialize a new chain using a federated peg script built from these public keys. And we'll be able to sign for it using these private keys, which we've just saved. One thing to note is that for this tutorial, we need to also be running a Bitcoin node. And the Bitcoin node will serve as the main chain, and this will be our sidechain. So for the purposes of this tutorial, I have a Bitcoin node, which can be accessed at bcli. And this is just a reg test Bitcoin node that I've launched. And if we look into any of the elements configuration files for either E1 or E2, so let's go into the data dir of E1 and look at its configuration file. We can see here that I have provided a main chain RPC port and a main chain username, which is what it needs to connect to this Bitcoin node. So just to summarize that, for the purposes of this tutorial, we have a main chain node running, which can be used in order to have elements run as a sidechain. Perfect. Now let's wipe the existing blockchain data and wallet data for both of these nodes. To do this, I will run rm-r and I'll pass in E1's data directory, which is located right here. And now I will run the exact same command for E2's data directory. Perfect. Now that the chain and wallet data has been deleted, we can use this public and private key, these two pairs, to generate a new fedpeg script that we will use. So what we're going to do is we're going to start the first element's daemon for the first node and pass in this fedpeg script argument. And this fedpeg script is the element script which needs to be satisfied in order for blocks to be signed. What this script will look like is it will be an element script which basically says provide 2 of 2 of the following keys. So it will be a 2 of 2 multi-signature script. So it will say something like 2 of 2, and then it will have the E1 public key, which we generated above, and the E2 public key, which we also generated above. And what will happen is that when we sign for the script, we just need to produce signatures with the 2 private keys, which we stored above, and then the blocks will be satisfied. Now, this is obviously written in English text, and Elements uses element scripts. This script needs to be passed in hex. I won't go into the details of how element script is constructed. You can read the documentation on that. It's quite similar to Bitcoin script. However, it does have additional opcodes. Nevertheless, I will just let you guys know that for this 2 of 2 multisig script, what we need is we need the following characters. And what I'm essentially adding here with the 5221, the 21 in the middle, and the AE. Well, let's surround the variable names here with brackets so that they are distinguished. And what we are doing here is we're kind of specifying the number of public keys, the number of signatures we need, etc. This is all in hex, but if you write out the raw element script for this 2 of 2 multisig and convert it to hex, it will look like this. So rather than getting into the details of that now, just take my word for it that this is a 2 of 2 multisig script, which says we need 2 of the following signatures in order to sign for these blocks and produce a valid block. Perfect. Now, just to confirm that this string I've generated, just to double check, it is the fedpeg script we want. Let me just echo that out. And we can see here that my shell substitutes these variable names for the 2 public keys we saved above. So that confirms that this is indeed the script that I am trying to write. Let me go ahead and start up this E1 node. Perfect. And now let's just confirm that this node is running by running some simple RPC on it. So let's run E1 CLI get block count. And we can see that E1 has been started. Perfect. Now let's confirm that E1 was indeed launched by issuing a simple RPC on it. So let's run E1 CLI get block count. And we can see a response of 0 indicates that, yes, indeed, this node is online and responsive. Now let's boot up E2 with the same network parameters. We can do this by taking the command we just ran and substituting the E1 for the E2. Perfect. And let's just ping this node with a simple RPC to confirm that it is indeed running. Awesome. Now we have started both of these nodes with this fedpeg script, which indicates that we need signatures from both E1's key and E2's key from those addresses we generated earlier in order to sign blocks. All right. Now, since we previously deleted the wallets of both nodes, the next step will be to re-import those private keys that we saved so that the nodes can later sign and complete the transfer of assets between chains and satisfy the requirements of the federated peg script. So before importing the keys, we're going to have to create new wallets since those wallets were deleted. So let me do E1 CLI, create wallet, and give it a name. And we can similarly run E2 CLI, create wallet, and give it a name. Now we can import the private keys with the import priv key RPC. So let's pass in that variable we created earlier, E1 priv key. And let's run the exact same command for E2. Perfect. We have now imported the private keys for both nodes for those two addresses. Now the next step is we need to mature some blocks on both chains. Maturity of blocks is a requirement of the peg process, as it protects against block reorganizations on the main chain, which would lead to an inflation of the pegged asset supply within the sidechain. Essentially, we want to make sure that blocks on the main chain are finalized before accepting peg-in transactions. Because if there is a reorg of a peg-in transaction and it gets reorganized out of the main chain, then we don't want to issue assets for that on the sidechain and have a discrepancy between the main chain funds locked onto the sidechain and the funds that are actually available on the sidechain. To keep this section focused on the federated peg, let me just generate blocks without using the block signing model that we looked at in the last section. So to do this, I'm going to return to using the generate command to create new blocks. So in order to finalize blocks on the Bitcoin chain, I'll need to generate first 101 blocks. So this is before any peg-ins can take place on the main chain. You will need at least 101 blocks. Awesome. And we don't necessarily need to generate any blocks right now on the sidechain and elements, but let's generate one anyways, because it's good practice in order to avoid potential inconsistencies. Perfect. Now our chain is ready to peg in. In order to peg into the chain, we need to generate a special kind of address using the get peg-in address command. Note that the duration between generating a peg-in address with get peg-in address and claiming it with the claim peg-in RPC should be kept as small as possible. Peg-in addresses are not long-term durable, and so they should not be reused. All right, we can do this with, let me just clear the screen. We can do this with E1 CLI get peg-in address. You can now see that this command creates a new main chain address as well as a new script that will need satisfying in order to claim the peg-in funds on the sidechain. The main chain address is a pay-to-script hash address that will be used by functionaries which are performing the watchman role within the Elements network. Like getNewAddress, the getPeg-in address RPC adds a new secret to the calling node's wallet, which in this case is E1. So, it's important to factor backup of the wallet file into your node management process. All right, with all that aside, we'll now send some Bitcoin from the main chain to the sidechain. Our main chain regression test wallets already holds some funds. So let's just check out how many funds it holds with the bcli get wallet info command. All right, we can see a balance of 5,100. This is what I have on my node. Yours might be set up differently and you might have a different balance there. Now we need to send funds to the main chain address our node generated earlier. Let's send 1 Bitcoin from the main chain to the sidechain. So we can do this by running bcli send to address. We'll provide this main chain peg-in address by copying and pasting it. And then we'll specify an amount. So let's do 1 for now. Now let's send it. We can run bcli get wallet info and see that this balance has decreased by a little more than 1. It's 1 point, a very small amount. And the reason why is that the 1 Bitcoin was sent and a tiny bit more was used for the fee of the transaction. All right. Now let's mature this transaction before the pagan will be claimed. And before it can be claimed, we need 100 blocks on top of this transaction. So that's one block which will hold this transaction and 100 blocks on top of it, which is a total of 101 blocks. We can do this by running b CLI generates 101. All right. We have just generated 101 main chain blocks and buried the pagan sufficiently. Now let's claim this pagan on the sidechain. To do this, we can use the claim pagan RPC, which with E1 CLI claim pagan. Let me just run that with no arguments just to see what it does and read its documentation. So if I run this, it will show me that claim pagan takes two mandatory required arguments. The raw Bitcoin transaction, which holds the pagan, and this TX out proof argument. So let's get both of those. The first thing we're going to need is the transaction ID of our pagan. If we scroll up, we can see that when we did the send to address for the pagan, we got this transaction ID. Let's copy that. And let's first get the TX out proof from this transaction. So this TX out proof RPC looks as follows. It looks like this. So let's just pass in this transaction ID I've just copied and get the TX out proof. As a matter of fact, let's put this into a variable just to make this easier. So we'll call this variable TX. You know what? We can just call it proof. So let's put this into the proof variable. And let's print it out. We have this proof. And next, we're going to need to get the raw transaction, which we can do with b CLI get raw transaction. And we'll just pass in that same TX ID we have copied from the pagan. Let's also store that in a variable, which we can just call, let's call it raw for raw transaction. And let's print that out, and we can see that we have this raw transaction. Perfect. Now recall, this claim pagan RPC takes the raw Bitcoin transaction and then the TX out proof. So let's go ahead and run that with E1 CLI claim pagan. We'll pass in the raw transaction and the proof. Awesome. Now we have this pagan claim transaction, which has been issued on the sidechain. This is the transaction ID for that. We can now check the balance of E1. It should not have changed, actually. So this balance will be what we had before. It shouldn't have changed at all because we have not confirmed this claim pagan transaction. So let's see what it is now. E1 CLI get wallet info. We can see that there is a balance of 21 million Bitcoins on E1. Let's go ahead and generate E1 CLI. Generate one. So we'll generate one block to confirm this pagan claim transaction. And now let's go ahead and check the balance one more time. Oops, wrong command. This one, get wallet info. And right here we can see that about one, of course subtracting a little bit for fees, one Bitcoin here has been added to this balance. So we have successfully pegged in. Now let's briefly go over the peg out process. The peg out process is actually quite similar in that an address is generated, funds are sent to it, and then the funds are released if the transaction is valid. I'm not going to cover the whole payout process. It involves work on the main chain, which is somewhat beyond the scope of this course. The steps in terms of the elements events are as follows. So if we want to peg out on elements, we first need to generate a Bitcoin address, which will receive the payout funds. So let's go ahead and run bcli get new address. Next, we want to just use the send to main chain command on elements with e1 CLI send to main chain. And we simply provide this address right here. And we'll provide an amount that we want to send to the main chain. Since we just pegged in one, let's also peg out one. So we can provide 1 BTC here. And we just need to generate a block to confirm that transaction on the sidechain. Now we can check the balance of E1's wallet. And we can see that, as a matter of fact, the balance has had 1 subtracted. So previously it was 21 million and 1 minus a bit for fees. And now it's back to 21 million minus a little bit that was used for fees. Perfect. So this balance has decreased. And then the final step, which we won't cover here, is that these funds will need to be claimed on the main chain. All right. In this section, we have actually seen quite a few things. We've seen how to generate a federated peg script, how to initialize a new chain that uses the script as a network consensus parameter rule, how to send funds from the main chain to the sidechain, then how to claim the funds within the element sidechain, and finally, we understood how sending funds back to the main chain is started. All right, that's all for this section. See you next time.